Calculus!
This is AP Calculus Lesson 7-2, Motion Integration. I am gone today because my daycare provider had a family emergency, and I can't do a crazy intro because it is about midnight, and I don't want to wake the family. Alright, let's jump right into the notes. Today's notes are super short. Integrating motion. So, by the way, welcome back. I hope you had a nice break. We can talk about it more on Wednesday when I'm back. So say I have this graph of velocity, and it's measured in feet per second, and I have time on this axis down here, probably measured in seconds, but it doesn't really matter that much. Here is my graph of velocity, and I'm asked this question: how much does the position change between time 1 and time 4? Alright, so here's the key thing that you need to know from today's lesson, which is in order to go backwards, if I have velocity and I want a position, in order to go backwards, look at the area between the curve and the x-axis, or in this case, the t-axis. So to go backwards, look at area, and specifically the area between t equals 1 and t equals 4. So if I look at t equals 1, which is right there, and t equals 4, right there. If I find the area of this shape, that represents the position change between t equals 1 and t equals 4. So there are a few ways to write that, but let me just go ahead and find that area, which is 1, 2, 3 by 1, 2, 3, 4. 3 times 4 is 12. This has an area of 12, which means I have a position change of 12, and then the units that make sense for position is feet. So the answer is 12 feet. 12 feet. And we know how to find this using algebra, or what the notation would look like. So let's get the general notation really quick. So if I have the integral between 1 and 4 of velocity, and let's just say we didn't know what the function was. In this case, we did know it because it was y equals 4 up until the point 4. But if I took this integral of velocity, this would look like, if I go backwards for velocity, remember antiderivative of velocity, I go backwards to position, and I'm just going to say position is x. This is going to be equal to x of t evaluated between 1 and 4, and if I actually plug those in, that's going to be x of 4 minus x of 1. And literally this means take the position, this is the position at 4, position at t equals 4, and then subtract it from the position at t equals 1. And that's really what we're looking for, right? The position change between time 1 and time 4, and that's literally what I'm writing right here. So it makes sense just generally. And then how to do it. When we actually have a problem, it looks like this. The integral between 1 and 4, and in this case we had our equation, which was 4. So our velocity is 4. I guess we would have a dt in here. I forgot to put a dt. If I take the antiderivative of that, then I have 4t, not 4x, because I'm with respect to t, evaluation bar between 1 and 4, which means I'm doing 4 times the quantity of 4 minus 1, which is equal to 4 times 3, which is 12. So our algebra does match our geometric way of answering this question. Alright, so far so good, but I want to talk about something in terms of why we're allowed to get to the unit feet. So we started with feet per second. Why are we allowed to just automatically assume we're in feet? I mean, you logically will say, well, if you're talking about position, you can't really be talking about feet per second because that's a unit of velocity. We have to just choose the correct unit. That's, I mean, your intuition is correct, but here's the more formal reason of what you're doing. And we're in this section right here. Why is the derivative of feet per second feet? So when you're really doing the integral, or this area under the curve, you're really breaking it up into an infinite number of rectangles. And we kind of skip over this in AP Calc for this curriculum, but this is really a Riemann sum, and I'm sure Sophia and Kaylin will tell you all about this because they're studying it more formally. But imagine you have an infinite number of rectangles here. I'm just going to draw it nice and big. Obviously, it would have infinitely small width here, but let's just say that's my rectangle. Let's go ahead and pull this rectangle out to analyze. So we're thinking of this rectangle in the graph, but in terms of let's color, oh gosh, blueberry I think was the one I chose. What is going on? I want a rectangle, yes. There we go. So let's say I pulled that rectangle out. So this rectangle, let's analyze its dimensions. So what was the dimension in terms of this direction? This is a unit of time, and specifically that's in seconds. What about this height here? What units did I have here? And you will say, okay, well that had a unit of feet per second. So this is feet per second because it was velocity. So if I was finding the area of the rectangle, the integral, each of these, I guess I got rid of that rectangle up there, each of these rectangles has an area, and what we really found was an area here, that 12 represents area. So I need to multiply these units together, feet per second times second. I think you can already see what's about to happen. So if I have feet per second, and I multiply that by seconds, then our units cancel out, and this bar, this infinitely small rectangle, has a unit of feet. So therefore we get feet. So kind of a cool little visual explanation of why our unit should be feet. Alright, so, and here is our really key thing that will be used on the homework over and over again. This is probably the 90% of what you're going to be doing on the homework. If I have some random integral between a and b of, in this case, a velocity function, I might be giving you acceleration, I won't give you position because you can't really go backwards from position. But if I have some integral, this guy right here means it's the total change in. Okay, this thing needs to be underlined in red like several times. Total change in. These words should appear no matter what. So on the AP test, on the test that I'm going to give you in my class, on the pretest, on all the fix-ups, if you see an integral and it says, what does this thing mean? If you see this word mean, you need to have these three words, total change in. And then, of course, you need to have the next correct word also, which will change depending on what you're talking about. But the total change in something. And then, in this case, you go backwards. So if I'm talking about velocity, then it's the total change in position. But if this was acceleration, backwards from acceleration would be velocity. It would be the total change in velocity. And then we need the next key part as well. From A to B, which, I mean, it's a definite integral, right? And usually you have to have units here. Don't forget your units. So you would say like from 1 second to 3 seconds or something like that. So you have to mention units twice because you have to talk units about this one too. What units is position in? So you have to have two types of units, the units for position and the units from A and B. All right, and you'll see that more. Let's just do a quick example. I know that I'm doing this out of order, but you'll see this right now. All right, so this is the homework. This is what it's asking for. Using the correct units, explain what this thing means. They just randomly gave us an integral. All right, well, I need to have those keywords. So it's the total change in, and then I'm talking about velocity, so if I go backwards, it's position. Okay, now what are my units? In, so if I have velocity, my velocity was meters per second, and then I get rid of a second because I'm multiplying by seconds, so it's just going to be in meters. You can say meters are just in M, because M stands for meters. And then you say from where to where? From 20 to 40. And what are 20 and 40? What units are they? 20 T, 20 seconds, from 20 to 40 seconds. And then you get full points. And I think just by writing that, you might either get 1 point or 2 points depending on the type of problem. But yeah, there's a ton of key things here, but every single time, total change in needs to be in your answer. So every time you are asked to find average velocity, it's the same 3 steps over and over. First, find the total position change. And, oh, look at this, total change in position. That is this thing right here. It's the integral from A to B of velocity, not acceleration, but velocity. So now you know how to find that. Find the total time change. I guess if you're speaking correct English, total change in time. And then finally you do step 1, which is the position change, this integral, and then you divide it by step 2, which is the total change in time. Alright, as a quick little formula, you have the change, delta means change again, change in position. Again, that comes from our integral over the change in time. And we know the change in position. Change in position, we have a general formula for that. It's x of the second point. So the end point is b in this case. So x of b minus x of a. All of that divided by the change in time. Well, those are the times. A and b are the times, so it's just b minus a. And does this formula seem familiar at all? This is the formula for a secant line, which also represents the average slope. This is average velocity, this is average velocity, average slope. It all comes together. In this case, we wrapped around and said, okay, you can use the integral to find that top part, the numerator. Alright, that concludes this lesson. I don't think there's a backside. There's not. Go ahead and write your summary now, and then you can begin on the homework. I'll see you guys on Wednesday.